Okay, now we can start. So I'm Ramanujam, and it's my pleasure to welcome you all to this webinar and this series of webinars on logic education. And this is being organized by the Commission on Logic Education, which is a part of the Division for Logic, Methodology, and Philosophy of Science and Technology. And that's a mouthful. So the commission is, as I was mentioning to Paul a little earlier, it's been around for a couple of years, and its objective is to really facilitate the introduction and development of education and logic and at schools and universities worldwide. And it's bringing together a community of logic teachers from different disciplines: mathematical logic, philosophical logic, theoretical computer science, and research logicians, logic teachers at different levels, and hopefully many at school level as well. So it's a pleasure to welcome Professor Paul Christian Dawkins of Texas State University. I believe it's the rising star of Texas. Well, yes. And he's here to talk to us today. He's a renowned educator, and he's been working on various issues in mathematics education, and especially in relation to logic. And there are, he has a he's a recipient of many prestigious awards and honors. I'm not going to list them here, but and several research grants, which is also very important. And but his research, especially on the language used by students and how in mathematics classrooms at undergraduate level, and how it relates to mathematical logic, is something of great interest, and that in this particular community we've been discussing. So it's a pleasure to have Professor Paul Dawkins talk to us. And over to you, Paul.
All right. Thank you so much for having me. Yeah. So I'm going to help contextualize the talk as I go along, I'm going to share a bit both about kind of the reason I come into studying logic, but also then the particular perspectives I bring that inform the way I do this research. But also I'm going to take you a bit on just a journey of my own learning about these issues as it relates to undergraduate mathematics. But I'm going to try to focus on, hopefully just to be of most use to most of the audience, I'm going to try to highlight some of the ways that working with students have really helped me to understand how their kind of naive or untrained uses of language really don't fit well. They kind of don't match very well with the ways that language is implicitly treated in logic. And I think this is often even at kind of very fundamental levels about assumptions of what a language is and what it does. So I'm going to hope to portray for you what I've learned about some of my students' ways of dealing with language that I think really helped me to see what is some of the learning that needs to happen for students to engage with logic. So it's a little bit more of a statement of the problem than the solution, but I hope it'll be useful. So I first want to acknowledge many people who've been a part of different parts of this project, people I've collaborated with. Some papers are just coming out here this year with a few of these graduate students, but also NSF has given us, the National Science Foundation of the US has given us some money to support this, which I'm very thankful for. So my goals for the talk are to share some stories, ultimately, kind of stories that were important for me to learn about student language use that I hope will be useful for you. So there will be 3 major episodes that I'll move through. The first one is about students trying to write a proof or produce a proof. The second one is about students comparing mathematical statements. And the third one is going to be about students comparing mathematical proofs. I think actually these tasks have also been really helpful tools in learning more about what's going on for students. So either way, I hope that those will also be useful to you. But the TLDR, which is internet speak for too long didn't read. So if you check out a little bit in the middle of the talk, here's the summary. that, student language use I have learned is very coherent, and it's rational, but it is just distinct from the way that mathematical practice uses language. And in many ways, actually, I've come to understand from a lot of linguistic theories how much mathematical language use is really kind of a funny way of using language, because there's a lot of parts of natural language we try to turn off or kind of ignore. So let me say a few things about my context and my goals. So first off, I'm a mathematics educator at the undergrad level in the US. So I would kind of say my intellectual and research home is the research and undergraduate math education community, which is in the US, or that corresponds, I know, in the European context to INDRM. But undergraduate math education is really my kind of broad focus. And within that, I focus though on proof-based mathematics. So since my dissertation, I've been interested in how students, so in the US context in particular, students don't encounter a lot of proof prior to about third year of undergrad. And largely, they don't encounter a whole lot of logic prior to that either. If anything, students may encounter logic in a philosophy class, maybe in a computer science class, but a lot of these are new ideas that come in quite late, as late as their third year of undergrad. And for a lot of American students, they are math majors, so they think of themselves as mathematically competent and interested. But then all of a sudden, proof-based math is this really hard left turn in their education that they find quite challenging. And so I'm really interested in that transition, how a lot of students navigate that and how we can help them with that. So that's really my home, is proof-based math. Um, so because of my background in math education, there's a few kind of theoretical and methodological tools that that orient a lot of the way I do my research. So part of it is constructivist research. And basically what that means for me is I want to build qualitative models of student thinking. And I want to build models as much as possible, or be able to describe in great detail processes by which students build new knowledge. And so I use teaching experiments. So a lot of the evidence you're going to see from in this talk today is evidence that I think has been sort of reinforced by classroom instruction over the years. But largely, I learned these things by working with students, often in pairs, in a laboratory setting, using either just task-based interviews or teaching sequences, like a teaching experiment, where I have a hypothesis of learning. I meet with two students for 6 to 12 weeks and try to take them through a learning sequence. But in particular, realistic mathematics education from the kind of Dutch tradition, I borrow some of their tools for instructional design, in particular guided reinvention. And guided reinvention, one of the reasons I really value it is if I can create a set of tasks that really motivate students to generate new knowledge to solve those tasks, and I can kind of, with a light touch guidance, guide them to reinvent key mathematical ideas. I don't always think that that's exactly how I'm going to practice in the classroom all the time, but it's an amazing research tool, if nothing else, such that if I can get students to reinvent key mathematical ideas with a pretty light touch guidance, then I'm going to learn a lot about what is it that students need to learn to generate that knowledge. What does that learning path need to look like? And in particular about logic, when I've tried to engage students in kind of reinventing key ideas of logic, it's helped me to understand much more what are the barriers, what are the aspects of how language is working for students prior to instruction that really need to kind of be changed or be reorganized to support them in reinventing logical ideas. And so that's a big piece of how I come at this research. And so my claim here is that not that everyone needs to teach that way or anything, but I really largely use this guided reinvention in constructivist teaching experiments are a great way to learn about what it is for me to learn, what students need to learn to develop these new forms of knowledge. And so I'm starting at a pretty primitive place in terms of the learning of logic, because I'm trying to get students to reinvent some of these ideas. So long before I was actually doing all of that, at the Park City Math Institute in, I don't know, 2012, when I was just in my second year as faculty. I was invited to this summer workshop that was a mentoring workshop for math ed faculty. And I was hanging out with my friend and colleague, Kevin Moore, and I was so impressed with the work they were doing, studying students' meanings for graphs and for variation of functions. So a very different context, but I was just impressed by kind of the paradigm of their research. And so I had this question of, well, in the proof-based setting, conditionals are all over the place. So what are students' meanings for conditionals? Meaning kind of implicitly, what meaning does a student bring to a statement by virtue of it being a conditional statement? And I should say I was very naive at the time about how much research was out there and from the psychology literature, the philosophy literature. But either way, I was interested in this. So I went back to my university and I got some students out of an axiomatic geometry course. And I was just kind of an outside observer. I wasn't really imposing any tasks, but it wasn't hard to find proving tasks that involved conditional statements that allowed me to kind of interrogate what structure do these students bring to these statements by virtue of their conditional form. And so I want to tell you a story about these two students that I these are all pseudonyms, but I call them Ovid and I think Eric. Um, sorry, no. Kirk is the student we're going to be talking about. Kirk. But either way, their names will appear on the screen here in a minute. So here's the task they were working on. They were trying to prove that Euclid's fifth postulate is true if and only if Playfair's postulate is true. So Euclid's fifth postulate is framed in terms of these transversal configurations. If you have two lines cut by a transversal, then if these same side interior angles sum to less than 180, then the lines will meet. And that diagram is taken from their textbook. And they were going to use that statement to prove, so they're proving one direction of this if and only if here, to Playfair's postulate. So given Euclid's fifth, they want to prove Playfair's, and Playfair says, given any line and a point, there exists only one line through the given point that doesn't intersect the given line. So again, my question was, what is their meaning for conditionals? And there's a background theorem they had already proven by contradiction here. Given two lines cut by a transversal, if the same side interior angles sum to 180, then the lines do not intersect. So they had that as a background. So notice here, there's lots of conditionals in this task. In fact, they're using conditionals to prove other things. So this felt like a perfect task for me to kind of get at what's going on with conditionals in this setting. So what Kirk taught me, Kirk and Oren, sorry, those are the pseudonyms here. Kirk taught me how misleading my question was. I would assume that Kirk was going to structure his reasoning about these tasks and these statements by virtue of their conditional structure. But I found that to not really be a good way to make sense of Kirk's, especially the structure of his argument for why EFP implied Playfair's postulate. That his structure for that proof did not really have a direction that was in any way dependent on the kind of a conditional statement structure and I account for this in some of these papers here that are cited. So I want to sum for you up Kirk's argument. Here's his argument that he was going to classify all the angle sums alpha plus beta. So now we've kind of given some variable names here in the diagram, so we can talk about the angle sum as alpha plus beta. And if the sum is less than 180, then the lines meet. If the sum is greater than 180, then the angle sum on the other side is less than 180 and the lines meet on that side. And if the sum is 180, then by the previous theorem, we know the lines do not meet. So this is how Kirk was summarizing what Euclid's fifth postulate tells us. And he would even hold his arms up in kind of imagining these, different possibilities. And so 7 times in this conversation, Kirk kept saying, there's only one instance where the lines do not meet. And so that was sort of his summary of what does Euclid's fifth postulate tell us about these lines? There's only one instance where the lines do not meet. And then that relates to Playfair's quite naturally, because so he said, if the angles add to 180 exactly, the lines will not meet. It's the only one instance where lines will not meet. So basically, there's only one time where the lines will not meet, and Playfair's postulate basically states there's only one instance where one case where the lines will not meet. So they kind of like either way, there's only one case. So what does either way mean? Either way is if I'm listening to Euclid's fifth postulate, what does it tell me? Only one instance. If I listen to Playfair's postulate, what does it tell me? Only one instance. Either way, only one instance. So therefore, they say the same thing. So we often assume in proving, if you're proving a conditional, you move along some path implicitly in logic or in space or whatever, or in time, from hypotheses to conclusions. But I would say that's not the structure that Kirk had for his argument. But in studying him, I really kind of was looking for that. And at first, I was a little baffled. I was kind of confused about why Kirk was so perturbed, because Orrin really was trying to build kind of a directed argument from Euclid's fifth to Playfair's. And he was having interesting trouble with that, but I don't want to distract too much from the point. But Kirk felt like all of Orrin's work felt very unnecessary. Kirk was like, we're done here because of his only one instance argument. And so I claim Kirk's proof didn't have a directional structure. It really, he just said, look, Euclid's fifth says only one parallel. Playfair's says only one parallel. They say the same thing, so they're equivalent. Done. And so in that argument, there's not hypotheses and conclusions. There's just two statements that are giving the same kind of account of what happens. So here's the way I would try to portray both of the statements are not proving each other in Kirk's argument. They're both describing what's happening. And since they describe the same thing, they're equivalent. So here is my kind of key insight that I'm going to then argue. I think this is an account of what's going on for Kirk, and I think it is a lot of what I've learned about a lot of other students in other settings that I'm going to share in the other episodes. For students, mathematical statements refer to states of affairs. So this is not a relationship between the statements and each other, or the statements and what they imply. These are relationships between the statements and what they describe. Statements in mathematics point to the world of mathematical objects. And if they tell us the same thing, then they're equivalent. And I would just argue that's a really different picture of what we mean by equivalence or proving one statement from another. It's a very different image of what the language is doing. So, some studies of logical reasoning. So notice, as a consequence of Kirk's argument, there's no direction. There's no if and only if for Kirk. There's just kind of coincidence between what they describe. And another instance of where I think we can sort of misconstrue student thinking if we just use our model to put on them is the way that a lot of prior studies have claimed that students think of conditionals as biconditionals. And again, there's a lot of nuance to exactly what people mean by these claims, but I think what's happening there is we're wanting to describe the student work using one of our logical connectives. And so since the student's thinking is not directed, we jump to the biconditional or the conjunction. People argue either way for different student instances of student work. But the problem is we're still wanting to use our kind of truth functional account to get at student work. And I just felt like none of those really captured what was happening for Kirk, because Kirk's reasoning was very descriptive of states of affairs. And so I don't think that the best way to model Kirk's reasoning is using any kind of truth value or truth functional kind of account of what is happening here. I would claim that imposes on Kirk's reasoning something relatively foreign to it. I've called this in writing, there's a paper from 2019 where I really tried to describe this kind of general idea, the pronominal sense of reference. And I say that to say that for students, mathematical statements and mathematical terms act like pronouns. They kind of point at stuff. If I say that, I'm really not telling you anything about that other than just kind of pointing at it, right? Pronouns kind of rely on you to look at whatever it is that I'm referring to. And I offer that as a way to think about what's really different about reference in the way mathematical statements work. Now, I've not called this example use because I've found for students the pronominal sense of reference for mathematical statements and terms can refer to a lot of things. Sometimes it refers to examples, sometimes it refers to a representation, sometimes it refers to a definition or a meaning, or sometimes it refers to a lot of things. So, but it still points to some aspect of the mathematical objects in the classes. Um, and I would argue that the way we kind of treat truth values often stand in as kind of a proxy for not needing reference, right? I mean, a truth value account of logic can kind of operate separately from a semantic account, even if we may wed them together. But for students, there's this natural sense of pointing to things. And so conditionals in this view are less implications between propositions and predicates. And often they're more descriptions of occurrences or co-occurrences kind of among objects. And so this is where we kind of get this very descriptive almost account of what a conditional says. And again, the literature from psychology and philosophy has a lot of different ways to try to capture this. But I think it's important to say our mathematical tools are just not adequate to model student thinking, even in a mathematical setting, even when students are proving. I think the psych literature and the philosophy literature have long said that formal logic, kind of the standard predicate or the standard propositional logic, is a bad model for how people reason in the everyday. But I think even in mathematical settings, we find that there's can be some disconnect. This is not true for all students, but it can be true even for a junior math major in the US at least. Another instance of what I think I'm trying to get at here, you can see it when in one of my classes we were analyzing these two statements, which are contrapositives and both true. And the student said, they're both true, but not at the same time.
Mm-hmm.
So what does the student mean when they say they're both true, but not at the same time? Well, this relates to the idea that what the student is kind of meaning is not only does the conditional need to be kind of not false or true, it needs to apply. So there are triangles that are acute, and those acute triangles are not obtuse. But the acute triangles are disjoint from the obtuse triangles. And so the second statement is about obtuse triangles, which are not acute. But because they're totally disjoint sets, no one triangle is going to have both statements apply to them at the same time. They're instead, and so this is the notion that, again, the statement is about the state of affairs that it refers to. And because these are about disjoint sets of triangles, they never are true at the same time. So my understanding of Kirk's reasoning helped me to say, okay, I need to approach my question from a new angle. Students don't just have a generalized meaning of conditionals that they bring to the table every time they work with a mathematical conditional. So if anything, what I wanted to then find out is, well, what would it take for me to help students develop or kind of generate the a systematic, single, unified, formal meaning for conditionals? Could I get students to construct the meaning of mathematical conditionals, or at least could I get them to construct a meaning of mathematical conditionals? So one of my ideas here, and this sort of came as I was thinking more and more about logic and sort of what are the roots of logic, from this idea that when we do logic, before we generalize to all such conditional statements, it would help if we at least compare two. And we say, does this one work the same as this one? And I started thinking about how we do this in argument a lot. So these are some instances of arguments I just pulled off the internet. But in all these cases, what you'll see is, I think there's something logical about these arguments, because what they're doing is they're holding up one argument and then they're giving you kind of a formal equivalent and saying, because the second argument is absurd and you shouldn't agree with it, that undermines your belief in the first. So I think the purple one is maybe a good one to look at first here. which is you may think there's no point in singing unless you're good at it, but that's like saying there's no point in doing anything at all unless you're particularly gifted at it, which is ridiculous. And so because here there's kind of a generalizing action, whereas this argument kind of in gold down here is more kind of just inverting the argument. When someone says you shouldn't be sad because someone has it worse than you, that's like saying you shouldn't be happy because someone has it better than you. Because you ought to reject the second, you should reject the first. So there's this idea of comparing arguments or comparing statements that I think could be the roots of learning logic, because it leads us to think about not just before you generalize the content of the argument into P's and Q's, you just kind of intentionally shift the content of the argument. So this was kind of an inspirational idea for me. So before we jump to general letters, I thought, what if I just give students a whole list of all mathematical statements that to me have the same logical form? And so all of these are either universally quantified or kind of non-quantified or statements. And so I started these experiments along, gosh, it was over 10 years ago now, where I started giving these to basically untrained students. I took undergrads who were ready to take a proof course, but had never taken a proof-based course. And I would give them these lists of statements and initially say true or false. But then as they determined whether they were true or false, I started inviting them to compare them, to say, okay, if you compare this statement to that statement, do they work the same or differently? Why? And started trying to get students to reflect on, should these statements all have the same form? And yes or no? And if they do or they don't, what does that tell us about or? So I learned a lot from getting students to just tell me what these statements do and don't mean to them. And so this again led me to questioning my assumptions. So first off, you'll notice the first two statements I gave students, I thought of as basically a generalized version and then a specific version. I would think of these as parallel statements. X is even or X is odd, and then the integer 15 is even or 15 is odd. Students could read this and make sense of it. But I had a number of students who, when I gave them these, they'd said the first of these is true and the second one is false. Now I'll just give you a few seconds to think. Why would students say the second one is false? Yeah. So this does not have to do with inclusive or exclusive or, because the second one should be true under either definition of or. And I think for a lot of mathematicians and computer scientists, we know that's a very important distinction among ors. But here, something different is going on for these students. So why would they say that second statement is false? I think there's two different accounts. One is kind of simpler, which is the statement contains a patent falsehood, so it needs to be false. And so in this paper, Dawkins and Cook, we kind of called that the part false, all false heuristic, where if you see a statement that contains a falsehood, then you just declare the whole thing false. And so it's kind of a knee-jerk reaction. That's not the most sophisticated reason. And the students who gave that reason, sometimes if you let them think about it, they would say, oh, well, the or maybe makes it okay. Because there's an or, one or the other is enough. But there's a more sophisticated reason that other students taught me, which is that the way to basically think of it is this. If I tell you that for lunch, I'm going to have fish or chicken, implicitly, I've told you I've not yet decided. Because if I tell you fish or chicken, and I've actually in my heart determined I'm eating fish, then that's just a weird way to speak, right? That's not how we normally communicate. And so for me to tell you 15 is even or 15 is odd is just a strange way to speak, because what should be the most appropriate way to communicate with someone in good faith, it's for me to tell you what I know, which is 15 is odd. And so this gets into the realm of pragmatics where A2, it's less that students were telling me it was false, but they were telling me I would never say that. I don't endorse this statement. I don't affirm this statement because it's not a statement you should make. If you want to communicate, you should say just 15 is odd. And admittedly, in logic, we don't to some extent care about A2. Maybe I shouldn't say in logic. In logic, we do. In math, we don't particularly care about statement A2, except as an instance of A1. And we view it as an instance of A1. But here's where it gets really interesting. From a pragmatic standpoint, A1 is a completely natural statement. And you need the or because across the range of integers, some are even, some are odd, but together, every one of them is even or odd. The or is completely natural and motivated in the first statement, whereas the or is really artificial in the second statement, taken on its own. And so from a pragmatic standpoint, the students were queuing in on something really quite reasonable about the difference between the quantified statement and the non-quantified statement. And that really challenged me to say, oh, okay, first off, you'll notice in my studies, I only use math language because I think logic makes the most sense in mathematics. And if I want students to generate logic, I was dubious about whether they would generate it from everyday language or from nonsense language. So I thought mathematical language was the right place to start. But even in mathematics, I had to admit that A2 is an unnatural statement to talk about mathematics, whereas A1 is actually a very natural and interesting statement to talk about A1 or to talk about mathematics. And I'll say it got even worse with conditionals. If you give students non-quantified conditionals, it gives them fits and they hate it. The other thing I noticed with students is that negative claims are weird. Again, I've got a whole paper on this, Dawkins 2017. I can't go too deep into this, but when students were dealing with these statements about geometric objects, this became really clear to them that or to me, sorry, in their reasoning, it became very clear that, for instance, something like not a rectangle felt sort of unfinished to them, or it needed to be unpacked. If you say a quadrilateral is not a rectangle, the students really, some of them at least, felt this, desire to say, well, what is it? If it's not a rectangle, what class is it in? Because they do kind of think about geometric shapes as kind of having natural kinds, if you will. There's like a natural taxonomy of most geometric shapes, and you name them via whatever species they are. And so they said, well, if it's not a rectangle, what is it? And so they would do things like, if it's not a rectangle, then maybe it's a parallelogram. But as soon as they would insert parallelogram into the sentence, it would actually change what the sentence says. Because as a class, of course, parallelogram is not equivalent to not a rectangle. In fact, formally, every rectangle ought to be a parallelogram. But the point was the negatives for them were kind of this piece that they needed to unpack. And so I found first off that when students read a negative predicate like that, they thought of it more like kind of saying X is not in the set S rather than saying X is in the set S complement. And we would treat those as formally equivalent, right? If you're not in S, you have to be in the complement. But this idea of forming a set that's defined negatively, like a complement, was not just intuitive to them. They didn't want to just immediately admit not a rectangle as a class of shapes. That was not an intuitive step for many of them. And secondly, then that led them to say, okay, well, if X is not in S, then where is it? They wanted to substitute a negative claim for a positive one because that allowed them to actually talk about the object with greater clarity. And again, I hope you'll see that all of this fits very closely with this idea that for students, mathematical language refers to states of affairs. They want to describe what's out there. And therefore, they would sometimes make these substitutions in the language that were not formally equivalent, but I could understand why they had that desire to do it. So again, this relates to this idea that terms and properties refer to objects that fit the term or have the property, or, and here I'm saying, even a thing like is a rectangle, to treat is a rectangle like a predicate, P of X, that has a truth value is totally weird to student language use because is a rectangle, it's not just that it's false for non-rectangles, it just doesn't even talk about non-rectangles. Like, you know, is a rectangle isn't a function that ranges over all shapes and gives them true or falses. It just only talks about rectangles. Again, this idea that the term just refers to the things that make it true. And so negative descriptions are illegitimate to students in a way. Like it's fine to say that guy's a lawyer, but if you're like, oh, well, that guy's not a lawyer, unless there's some pragmatic reason why you would ever say that. I don't think of myself as being in the international club of all non-lawyers. I mean, we just don't think about negative categories in the same way. So this raises this question then when we try to teach truth values, that even truth tables don't match what's going on for students with language, because for students, the language only talks about the things that make true. And therefore, the rest of the truth table is really this kind of artificial add-on that just isn't matching what's going on for students initially for them. And again, I'll mention later, it's not like students can't reason about this. I'm just trying to give you a notion of, for students, when they're coming into these experiments, what's really on the table for them in the language. And this is even in math language. And even when I give them the task, true or false, still, all of that, the language is just operating differently for them than it is for me. So I might even, push this little provocative point here briefly. How much do truth tables actually capture what math language means to mathematicians? So according to the non-quantified truth table, that's a tautology. And we all know that that's not mathematically. We don't want for any two predicates P to Q for that to be true. And this relates to the idea that, years ago, one of my philosophy colleagues at Northern Illinois told me, he's like, look, for you mathematicians, conditionals aren't conditionals. Your conditionals are universals. It's a different thing. And similarly here, this Intro to Proof textbook by Hamack argues, when we give you a conditional and their predicates, he kind of clarifies when there's an open sentence here, if they're predicates, then just implicitly, we always assume a conditional is universally quantified. That's just basically how we use conditionals. And so here in the book, they're kind of saying, look, I'm going to leave off the universal quantifier because we don't always want to say it, but it's implicitly usually there. And if you add the universal quantifier to this statement up here, P implies Q or Q implies P, to kind of a meaningful mathematical sentence, then, with universal quantifiers, it's no longer a tautology and you avoid the kind of counterintuitive notion. So what's my point? I found that for students, quantified mathematical language was much more reasonable for them and much more kind of intuitive for them than non-quantified mathematical language. But when we teach logic, we often want to start with these non-quantified sentences that are admittedly quite, artificial. And we want to say that, the quantified statements just derive from the non-quantified, but that's very contrary to how the language works for students. And I might even claim it's a little bit backwards from how we really want to think about the language if we're just doing math. Now, I admit I'm in a group here of logic educators, and so I understand that if your goals are about logic and not just doing mathematics, there are good reasons why you want to define things the other way. But given my goals of really just getting students up and running on proof-based math, this is kind of a gloss I may be willing to countenance more than some others. Okay, so let me then talk about some ways that I actually think those student intuitions are, again, subtly distinct from ours, but are worth exploring. So I would have things happen like this, where if I gave students this conditional statement, and again said true or false, students would rightly say this is a false statement, and they would give a counterexample. So they would say 15 makes this false. And if I said, why does 15 make this false? They would say, well, it's a multiple of 6, or sorry, it's a multiple of 3, but not a multiple of 6. Now, to me, as a trained, mathematician and someone semi-knowledgeable in logic, that sounds like they negated the conditional. That sounds a lot like P and not Q. So I wanted to think, oh, wow, they very intuitively can negate the statement. But I found that that's not what's going on for them. In fact, often if I would ask them to kind of generalize the statement they just made, they almost couldn't reproduce that statement very easily. Because what students were doing when they said it is a multiple of 3, but not a multiple of 6, is they were simply describing why is 15 a counterexample. But they hadn't yet kind of decoupled that description from the object to say, actually, that's a generalized description of what would be required of any number to be a counterexample. So with a little help, though, students can be led to kind of generalize that condition. What would it take for any number to be a counterexample? Well, it would need to be a multiple of 3 and not a multiple of 6. And so you can get students to kind of harness their descriptive activity to generalize it to this other idea of describing a counterexample. But and then from that, you can then kind of quantify that condition to say, well, what happens if there exists such a number? Well, then you have the kind of sufficient conditions for negating the original conditional. And so this all of a sudden becomes a new statement that actually opposes the original statement. But what I've become pretty convinced of by trying to get students to reinvent these ideas over the last years is that students don't have really a naive notion of what we would call the negation of a statement. And the reason is because the negation of a statement is a relationship between two statements. And what's much more intuitive to students is a statement and a counterexample, because like, once again, for students, statements refer to states of affairs. So what's good here is that their intuitions of counterexample can be harnessed to build the idea of a negation, but they don't just have this idea of opposing statements. And I've actually found that defining the negation in general is a really slippery notion. I mean, I think most people just kind of gloss it and say, well, if you put "it is not the case that" in front of any statement, you get the negation, and then you kind of come up with basically formal equivalence. But it's a really subtle notion to try to just describe to someone offhand. And I don't think students really just come in with a naive notion of what is the negation of a statement. And I think that this account I'm giving of the pronominal sense of reference helps us understand why that's not just a primitive intuition, but it's one that students can apprehend with just a little bit of guidance. Another just kind of interesting note here is, of course, then if you just quantify this and say, okay, does there exist any object that is a multiple of 6 and it's not a multiple of 3? If you kind of state the conditions for a counterexample, this is also pretty tantamount to proving by contradiction. That basically, if you show no such object exists, that's why contradiction it's one account of contradiction in this specific case of conditionals. But either way, that's a little bonus connection. So yeah, again, students understand counterexamples as a relationship between a statement and a referent object. And I've found that as a very intuitive kind of universal thing that a lot of students have in their ways of thinking about mathematical language. Negation and implication are for us relations but among statements, and that is just not as intuitive. And this is really important that when we listen to students in kind of their untrained language use, every time they may draw upon language that for us has this very formal meaning. They may grab if then from their kind of language repertoire, or even for some, or usually they won't say there exists in English, at least not my students, maybe some do. But they'll grab these bits of language that math has appropriated, but that doesn't mean they have a generalized notion of what that language means. They haven't systematized it yet. And so they are, again, drawing on language to describe states of affairs, but that doesn't mean that the language they use is part of a generalized class of all statements of that type. That's this really abstract idea that, again, students are capable of learning. It's just not one that, so as I'll say later, logic answers questions often my students haven't asked yet. And so they need an opportunity to think about this idea of the class of all statements that have this form. So to teach logic, my claim is we need to invite students to think about and compare the structure of statements and how they refer. How is the reference structure of all if-thens in some sense the same? And students can totally answer that question if they know that's the question they need to answer. I think I'm going to skip that part because I think I'm running a little bit short on time. Okay, I want to share with you this last bit of data that for me has been really challenging and compelling in support of my general thesis about the way statements refer to states of affairs. So in some later experiments, we started asking students to compare different proofs of the same statements. So what you have here is on the left, the conditional is the converse of what I showed you earlier. If X is a multiple of 6, then it's a multiple of 3. And we gave students 3 proofs related to that statement. One is a direct proof, one is a disproof of the converse, and the third is a proof of the contrapositive. And then in the second case, we gave them a conditional that is true biconditionally. So theorem 2 over here, if X is a multiple of 2 and a multiple of 7, then X is a multiple of 14. That's true biconditionally. So accordingly, what we showed them is proof 2.1 over here is this is a direct proof, and this is the proof of the converse. And we wanted to know, we asked students, okay, read the proof. The proof is clearly, relevant to the theorem, but the question students had is, does this proof prove the theorem? Why or why not? And our goal would be for students to recognize, and by some means, that the converse proof should not prove this theorem. Now, one of the options for why the converse proof doesn't prove the theorem is because notice over here, proof 1.2 is a disproof of the converse. And so clearly this conditional has a false converse. So students might formally say, well, then this theorem might have a false converse. So the converse is kind of a different thing. And again, going back to the same Introduction to Proof textbook that I like by Hamack, it's a great book in part because it's free. But Hamack makes this exact argument to students. Hamack presents students with one conditional with a false converse and basically says, look, because at least one conditional has a false converse, then in general, we always need to treat converses as separate things. The conditional statement Q implies P is called the converse. So a conditional statement and its converse express entirely different things. So my question is, do students buy that? Hamack makes this argument because one state conditional has a false converse. All conditionals are independent of their converse. Okay, so to test this even further, I did another modification where I took theorem 2 and all I did is just swap the numbers. And so this is the exact same theorem and 2 proofs, but I swapped the numbers 2, 7, and 14 with the numbers 4, 6, and 24. But now the theorem is false, proof 2.1 is invalid, and proof 2.2 is still valid because the converse is still a true statement, but now the theorem is false. So these proofs are as formally similar as they could be. Exact same structure of the proof, just change the numbers. So again, I wanted to know, would this problematize for students the very common claim that a lot of students do want to say that this converse proof does prove the theorem? Okay, so I'm going to tell you about 2 students who are, we've run this experiment now a number of times, but I'll tell you about 2 of the first ones I ran this experiment with who taught me a lot. Now, first off, the ways they were thinking were complicated in good ways. April did think that the converse proof proved the theorem because April basically said, well, look, if X is a multiple of 2 and 7, then I can represent it as 2 times 7 times K. And then, of course, if you put the 2 and the 7 together, that's 14K. So that means that, if it's a multiple of 2 and 7, it's a multiple of 14. But notice this equation doesn't give any direction. It's not like if this, then that. This equation is symmetric. And for her, this relationship became symmetric. So, if 2 and 7, then 14, if 14, then 2 and 7, again, there was just kind of this identity there. And so April said direction doesn't matter. Mariah, on the other hand, was imagining this proof in terms, she was a computer science major, and she was imagining writing like pseudocode here. And for her, one of the proofs was a single loop, and the other proof was a nested loop, and they were different. And so either way, so because the code had a different structure, Mariah said, nope, proof 2.1 does prove the theorem, proof 2.2 is a different thing. So either way, there's kind of complicated reasons why she thought of it differently. So after they had worked through all this and I'd presented the modified proofs with 6, 4, and 24, we were kind of summarizing now. And I drew this diagram on the board to kind of try to help them focus on, okay, does the kind of formal parallel between the proof with 2, 7, and 14, and then the modified proof with 6, 4, and 24, does that formal parallel matter to you at all? So the blue arrows here are Mariah's judgments. Mariah said, the converse proof proves the converse, but not the original theorem. The direct proof proves the original theorem. We know the changed proof is invalid. Either way. But April, her judgments were in green, and April had said proof 2.2, the converse proof does prove the theorem, even though when we change the numbers, we don't want to say that the converse proof proves the false theorem. So, I put this up in front of them and I'm asking, I said, okay, so April, last time you believed this, meaning this diagonal, that the converse proved the theorem. The converse proof proved the theorem. She said, yes, I still do. You still do. Okay, good. Okay. But just because of how the numbers are. Okay, just because how the numbers are. Okay. But switching up the numbers, you end up with new theorems, then no. So she's saying if all I change are the numbers, that changes how the proofs work. This doesn't bother you about the original set of numbers. You anticipated my question. And she said, I see how this works, waving at the board. So just changing the numbers, because stuff is different down here, doesn't mean you question when the numbers are 2 and 7. She's saying, yeah. So in other words, if all I change about the theorems and the proof are the numbers, which proofs prove which statements fundamentally changes for April. Now, I would argue this is directly contrary to Hammack's argument that if we kind of have one instance of, a situation, then that means we kind of, in general, statements that have this relationship have to obey certain rules. So here's my summary of what I think is going on for April. And we've had a number of other students affirm this same view. This came out in a very recent article. I'm still really challenged by this data, but I kind of love it because it puts a big roadblock in my way. For student, if you're in a conditional relationship that's not biconditional, so like theorem 1 and the modified 2, 4, 6, and 24 case, in that case, converse proofs don't prove the original conditional. But if you're in a biconditional relationship where you know that in fact the sets are equal, the properties imply each other, then converse proofs do prove the original statement. The rules of how the proofs work are different based on what you know about the states of affairs. So once again, for students, mathematical statements and proofs refer to states of affairs. And if what I know about the underlying predicates and properties and sets is different, then the proofs work differently. So one of the most fundamental ideas of logic is that, all proofs of the same form or all statements of the same form ought to have the same kind of properties and structure. They ought to work the same. And students don't just have that intuition, is what I've been confronted with by this data. And again, if you want to know more, read Tucci, Dawkins, and Rowe that just came out recently. Okay, so here's a summary of what I think I've tried to argue. Logic, by replacing mathematical content with truth values, misconstrues how language works for many students. Logic doesn't have to be so incompatible with student language use. And so I think that first off, if we do a semantic account of logic based in sets, we can make logic more compatible with students' naive language use. But a lot of people would probably be committed against such an approach. But at the very least, what I'll say is if we invite students to compare mathematical statements of the same form, and if we invite them to compare proofs that have the same form, they can very quickly get engaged in the activity of logic, which is what is the same about these statements by virtue of their form even when they talk about very different kinds of mathematical objects, they can understand that question and engage in it. And we need to give them those opportunities, is kind of really at the heart of what I care about. But we just assume all statements and arguments of the same form share key properties. And I've just found we can't take that for granted with students naively. And again, I think for a lot of students, just logic is answering questions that they haven't yet asked. And we need to invite them into the question before we offer them our answers, is I think a very basic outcome. Okay, so real quick, what are some key areas that can be explored? And I'm going to try to wrap up really fast. I know we're here about at time. Statements having truth values is really kind of a different account of how language works than describing states of affairs. For also, when we ask are statements true or false, that's different from the way we use language, because normally when you make a claim, not in logic or even in mathematics, simply saying something is tantamount to asserting it. This is kind of a pragmatic axiom. And again, that's just a way that the way logic wants to treat language just fundamentally doesn't fit with the way language works in the everyday. Negatives, as I pointed to, are really weird for students, and they just benefit from opportunities to think about how negation works and negating predicates. But moreover, it's really interesting to me to explore how do students engage in the process of systematizing mathematical language when we give them that opportunity. That's really what a lot of my experiments have been about. So I want to finish with a caveat, lest you misunderstand me. Students are utterly capable of learning all these things. I'm simply saying they aren't just naively available or inherent in how all of our students approach these things. So I don't want you to think that I'm saying, oh, students are incapable of anything. I just think they don't understand what problem logic is solving often when they begin these activities. And I would argue that different ways we present the logic may put bigger or lesser barriers in front of them. And moreover, it might help them to point out the ways that we're turning off a lot of aspects of everyday language, such as pragmatics. So either way, I'm going to wrap up there. Thank you. I really appreciate your time. And here's some references of some of the stuff I talked about.
Thanks very much, Paul. Thanks for that very thoughtful talk. So I think, yeah, Sarah has a question. There is also one question on chat that has been around for some time by Divakaran. I'll just read the question.
Yeah, so giving a name to the negation change the attitude. Yeah, so I think that this issue of whether students are comfortable with negative categories does differ by content. There's often kind of a contours to the different topics that you talk about, and students may be more or less familiar with it. And again, I'm talking here about kind of a primitive intuition. I think when you talk with students about, when you put it in front of students to treat a negative category as a set, when you kind of build the complement, I think a lot of them are just going to say, well, that's a non-obvious step, but it's not a terribly hard one. But it is something that we need to kind of motivate and justify. Why would we do that? And I think that's also where getting into things like even contrapositive equivalence, there's multiple intuitions there about the way things refer to objects to point out why would actually a conditional have anything to say about that contrapositive statement when the contrapositive statement is about a disjoint set of objects. And so helping them to say, yes, the complement set is a set of things that we want to treat as just as legitimate. We can then kind of show them that there's immediate value that we can gain out of formulating complement sets, because it allows us to discover these new ideas like contrapositive equivalence. So I think, and you can give names to it, but obviously at some point we like the convenience of just S complement. That's a great name for it, or not a prime. We don't need to actually give it like a new name or something. But yeah, Sarah.
Yeah, Sarah.
Yeah. Thanks. This was absolutely fascinating. I do most of my logic teaching in a philosophical context, and so I try to stay away from the math for all of the math phobes. And so I've jotted down a bunch of references to see the extent to which some of these things that you've talked about might also show up on the natural language. But lots of questions. I think the one that I'm going to ask is actually related to what you were saying just at the very end. Uh, when you were interrogating April and Mariah about kind of the differences of which proofs actually proved the theorem, and you mentioned that it involved the difference involved what you know about the states of affairs. And I wonder to what extent you have tried pushing them on this kind of epistemological point, which is, well, like, how do you know that the 2714 case works because the state of affairs is a biconditional and the other case is not? Because I wonder what they would say when kind of presented with this seeming circularity. Like, I know that the proof works because of the state of affairs being described, but as a logician, I want to come back and say, but how do you know that what that this sentence describes this state of affairs until you've done the proof?
Yeah, right. And we have one of those experiments where the pair really nicely kind of differed on that exact point. One of them really wanted to kind of say, because we know this is what's the case, then the order doesn't matter. And the other student was really bothered by this. And we did have kind of a pedagogical intervention that allowed them to, I think, confront that more fully in a way to say, basically, we rewrote kind of a new pseudo proof in which basically in the proof it almost says, but we already know this is the case. And when you state it that baldly in the proof, does that bother them? And to some extent,
Yeah.
it did evoke some of that perturbation that are you just kind of assuming you already know what you're proving? And if so, then what are we even doing here, right? So yeah, we did run into that. And I think this is one of the tensions we run into from a task design standpoint is for students to track, it's really complicated for them to read these whole proofs and try to be then thinking about their structure and comparing them across different number theory settings. Then we also later give them geometry or, we're changing a lot and we still want them to hone in on the signal and all the noise, which is the structure. And
Hmm.
so we've chosen not to give them terribly unfamiliar content where they don't know, where they're truly uncertain. But that's, of course, the other thing people often bring up is, well, what if you put them in the case of a theorem that's truly uncertain? They don't know the mathematics, so they don't know what ought to be the case. Would that help motivate it? And the thing is, that's just kind of contrary to some of our other goals of helping them really build these ideas of structure and direction. So yeah, we've worked on different kind of interventions, but yeah, your point is, I think, very appropriate because at some point you say, well, what does even proof mean? If you're bringing in what you already know, and yeah, but we did have a student who would go pretty far in trying to defend that view, but thankfully their
Yeah.
interview partner was willing to challenge them on it. So it gave us some interesting data to think about.
Awesome. Thank you.
There is another question on chat. This is from Jeenat on, can you see it or should I?
So yeah, math is considered helpful in knowing or learning logic. I mean, yeah, so if you just let me armchair philosophize, I would claim that logic grows out of mathematical practice at its roots. I think a lot of logic has really taken math as its paradigm and wanted to kind of mathematize language. After we've mathematized all the stuff we're talking about, what if we can even take our language itself and mathematize it as much as possible, right? The classic ideal of a calculus, right? A calculational language. And so I do think there's a natural way in which actually, yeah, psychologically, maybe logic often builds on math reasoning as opposed to the other way around. But that's a kind of high-minded idea. There is some evidence from Attridge and Ingalls. Some people have studied this in various ways. It's a hard problem to study. One of the ironic things actually is that mathematical training, depending on what task you use for people, mathematical training does seem to support people in drawing the modus ponens inference, in suppressing the converse inference. So learning math is very good at helping people distinguish a statement or an inference from its converse inference. But often math learning actually suppresses modus tollens in certain experiments, which is rather surprising. And if you wanted, I could maybe send you the references by which I'm making that claim. But yeah, people have tried to study this in general. So no, I don't want to push back on the claim that mathematical learning supports logic learning. I think that they often are quite mutually supporting, but it's not just a simple relationship.
Okay, I have a couple of questions, Paul. One is, do you see any difference between spoken statements and written statements in the kind of analysis that you're talking about? Of course, when it comes to comparing proofs or this kind of lengthy ones, it's slightly different. But earlier, when you're talking about single statements, because at least I see quite a bit of difference in the way students talk and the way they
Yeah.
and mathematics is largely a written language, and here we are talking about discourse. So how do you find this difference and how it playing out in the kind of essential points that you're making?
Yeah, so there's one thing I'll say kind of more broadly on what you're pointing out is, in math, not only do we often work with statements in this kind of written and very structured form, but I mean, we actually treat mathematical statements have agency, right? I mean, mathematicians will say things like, this theorem tells us, right? The statement is a interlocutor almost in the mathematical work, right? So you're right. I mean, statements take on this really powerful nature in mathematics, that students are kind of getting just introduced into that way of thinking about statements as entities that have this kind of power or agency or whatever you want to say. But I think certainly also what you said, when I'm speaking, I am not having to actively think about the grammar of my statements, right? I have subconscious processes that are managing all that grammar. And similarly, students will use a lot of language, especially in the verbal, that again, as me, as the expert hearer, I will hear the logical structure of their statement, but often they are very unaware. And so I've often found one of the things that you need to do with students is when they speak, say in class, I try to take the statement they just said and write it on the board so that they can kind of, because it's also a lot of working memory to both say what you want to say and then think about the way you said what you want to say and think about, are there other ways to interpret what I just said? I mean, that's a lot to keep in mind. So taking what's a student verbalized, writing it on the board so that then they can think about it again, is a really powerful tool for helping them reflect on the structure of what they said. And, I now take it for granted because I'm in a math department and I'm around mathematicians. But I think this is almost just a habit that mathematicians develop. It's so common that my colleagues will say something, listen to what they just said, and realize, oh, that was slightly imprecise. Let me try again. And they'll restate what they said to make it more, logically precise. But it's almost like the act of articulating, going from a meaning to an articulation is a bit separate from the act of then taking a statement and trying to interpret it. And often when you reinterpret your own statement, you realize, oh, it could be interpreted in other ways, or like it's not always a one-to-one kind of thing. And that's often what we want in mathematical practice is this tighter one-to-one matching between a meaning we want to convey and a articulation of it. And I think helping students write it down is a really important step in helping them reflect on the structure and how that makes the meaning of the statement or doesn't. So I don't know if that's sort of your answer or addresses your question, but that's also why we do give students a lot of written statements, put them on the board, because we want to give them that freedom to talk about them, analyze them. When someone else is interpreting the statement differently than I am, can I look at that statement, reinterpret it the way they're hearing it? It's very hard work for students to engage in that process. But I think those are all really important stages in learning logic. Learning to think about the structure and the meaning of the statement, and how those two interface in tight ways. Yeah.
So I had one more question. Probably it's related. I mean, much of the discussion that um, yours as well as other related literature, it's largely on proofs and where you see the role of logic. But what about other activity like defining or deriving, where again there is reasoning and implicitly logic is figuring, especially the difference in quantified and non-quantified statements, conditionals, all these things appear. Would you say that the role of logic is, or lack of it, or all the things that you've been talking about, would it be similar in those contexts as well, or is it specific to proving? So, yeah.
Yeah, so I mean, certainly defining is important. And some of my earlier work was on defining. I mean, right. So, I mean, logic doesn't work if you don't have well-defined statements, right? I mean, if there's not a clear, clearly defined reference set for a given predicate or, condition for a class, then you can't do a lot of the stuff we like to do. So this idea that we want both necessary and sufficient conditions for being in a class, the ways mathematicians treat definitions are certainly lurking in the background and are very important. And I think that's also why negations are special in mathematics. If you say not black in sort of talking about color, people might say, well, maybe it's white. And Aristotle, I think, even defined this distinction between what he called a contradictory and a contrary. So black and white are contraries because they can't both happen, but they're in mathematics, we always want the specific property of being contradictories, which is both mutually exclusive and together exhaustive, right? The property that gives you complement sets. And so that's another piece that plays in here, is that we want negations. A negative condition needs to correspond to the complement set of objects. And that's actually both a really important thing students need to learn, but it's also a really useful tool to helping students learn about why do we define things the way we do and how do we negate statements in really precise ways. So yeah, I think defining becomes really important. I mean, I think one of the questions I have that I don't know how to answer is in a lot of countries, there are kind of basic logical instruction given, say, at the high school level, or maybe even earlier. I think on one hand, the tools I use, this idea of comparing statements with the same form to say, do they work the same or not? Why? I think that could be a really powerful tool for teaching logic. But your end goals of what do students need to get out of that are probably quite different than my setting. Because again, I am trying to get students into proof-based math. But I think the notions of speaking with clarity about what does a statement mean, what does it not mean, what would be sufficient conditions to argue that it's false, all those are probably relevant to the K-12 classroom. You want to have agreement about what verifies and what falsifies. And I think that some of these basic tools could certainly be adapted very easily to other settings, even if you're not doing full-on proof, even if you're just justifying or arguing or just trying to speak with clarity. So I certainly think there's a lot of crossover, but I think exactly what crosses over would just depend on where you are, what your goals are. I mean, I don't think I've, especially talking to such an international audience, I don't know what all you teach to whom and why. And, there's so many parameters there that I'm unaware of probably.
Thank you. Thank you very much. Okay, I think if there are no other questions, yeah, let's thank Paul for a lovely talk, very thoughtful, and make us discuss many things more in times to come. So thanks very much, Paul. I've also on the chat, I have put a link to the commission webpage and to subscribe to the mailing list. So for those, so to please pass the word around, and I think we would be very happy to welcome more people to our Logic webinar, Logic Education webinar series. Thanks very much. Thanks everyone for coming and sharing in this webinar. Hope to see you again.
Jam, could you also tell us where we could download the recording if we want to?
Yes, I think we will. So the thing is that we'll put it up on the commission website, and which is there in the when we announce the talk, and it will go on YouTube, and the link will be placed in the commission website. Yeah.
I'm also happy to share the slides if people just.
That would be very nice. Yeah. Thank you,
Yeah.
Paul. Thanks very much.
Yeah, thank you all so much. It's great to get to meet you all, even if briefly. So.
Yeah, thank you. Thank you very much. Hope to see you again in more of our